All right. Sorry, I was going to be ready a couple minutes ago. My dog kept barking. I figured I didn't want him distracting. All right, so we are going to be finishing 1.6 today as well as starting 1.7. Your due dates for current homeworks can be seen. 1.5 is due today because we finished it a week ago. We will finish 1.6 today, which means its homework is due in 1 week per usual. A lot of y'all are doing a great job keeping up with the homework, so that's awesome. If you're not in that category, please try to be awesome in the future as much as possible. And then I do believe that this is going to be the range of dates for our first test. If I have not mentioned it with this kind of online format of things, I like to give 2 days to test in case a student has, something in their schedule come up. Obviously, we don't even count your attendance fully as just attending a class. It's part of your homework and everything due to, looser schedules and everything. So I like to kind of take that into consideration for the test as well. Now that's only for the regular tests. The final exam, when we get to it, that will be 1 day only. We will talk more about the test either next class or the class after that. But just as a warning, this is what it looks like your test dates will be unless we have some random snow day or something. That being said, we don't really have much to add. We can just go ahead and get into the lecture. And again, we're going to pick up where we left off in 1.6 with a quick kind of summary of a few details that were covered before.
Just kind of taking a minute to reiterate what we did last time in this 1.6 section, which we call other types of equations. This isn't every other type of equation in the world, not even close to it. But we did focus on polynomials, which we said the only way we'll solve polynomials higher than an x squared or an x cubed in here are solved by factoring. We did some examples, well, an example, because we'd already basically done some of those examples in the past. We dealt with radical equations, which were equations with square roots. You've got to learn the lingo in here. Radical, square root, or cube root, same thing. Radical, root. They both start with an R. So that might help you a little. And then with a lot of these weirder types of equations with a weird element, we say that we first of all need to isolate the weird bit. So if it's got a square root, isolate that. If it's got an absolute value, isolate that. Then the general idea in algebra is to undo the weird bit. So the opposite of a square root is to square both sides. And we said there's no plus or minus needed with this. The plus or minus is when you have something squared equal to a number. That's when you do this plus or minus. And I've said that you have got to remember when to do this. Historically, not just in pre-calculus, in classes past this, this is a common issue that people forget when to do a plus or minus. And it comes up later as well with the rational exponents. So again, that the plus or minus was not needed for the square root, but if you do check all your solutions, all of the negative ones would fail. So that's at least a little nice, I suppose, if you do make a mistake, as long as you're making sure you check them. All right, we had one simple example and one complicated example. Hold on one second. Then we went to rational exponents, which we said rational exponents and radicals are literally the exact same thing. All the rules that apply to radicals apply to rational exponents. That's something we mentioned in passing. Day one, we said that that was prereq material, so practice that stuff if you need to. But we said with equations and solving them, you need to isolate the weird bit, like this x to the 3/4. And then to undo it, well, that's a fraction. If you multiply that fraction by its reciprocal, you get rid of it. So that's why we say to raise both sides through the reciprocal. But we did give an if statement. So this is not a every time, this is half the time really in general, but not necessarily for our course. If the original numerator in the exponent was even, then you'll need a plus or minus. And we said that that was basically the same thing as having an x squared equal to a number because the numerator counts as the power. So an even power means undoing it, you need the plus or minus. I did not do an example with that. You might see one in your homework, but I did give you the instructions. Remember, in a pre-calculus setting, we don't give every single possible scenario in the lecture. First of all, we don't have that much time. We'd only go through a third of the material of the course if we did that. And then we did absolute value equations, which are pretty simple as long as you remember that there are generally two answers and not one, because generally you end up in this isolate the absolute value, set the inside equal to the number, set the inside equal to the opposite of the number. Now, that sometimes will get to these weird cases where if the number by itself, once it's isolated, is negative, you can't have something that's positive equal to something that's negative. Absolute values are positive, negatives are negative. So you can get false statements, which are no solutions. We also saw an example where the solutions were overlapping. They were repeated roots as we've come to know them. And we'll study further in chapters 2 and 3. So sometimes you only get one answer. And then we gave you, I believe, the instructions for a minute or two. Yes, we did, for equations in quadratic form. So this will be the last topic of the section. This is, I would say, the most interesting topic of the section because it's probably the one that we'll use the most going forward in this course and in Calc 1. Now, I'm not saying that absolute value equations aren't seen. They're seen all the time, especially in Calc 2 and moving forward. I'm not saying that radical equations aren't seen with some kind of frequency in another later math class. Just not really too much in the rest of this course. But this quadratic form idea, this substitution idea, this idea of using a substitution to break down something that's more complicated into something that's simpler, like taking a problem that goes from dollars to yen, and I'm not saying that yen are simpler than dollars. Yen is simpler than dollars. Not sure the singularity or plurality of there, but doesn't matter. It's just that this is a way of changing things to a different set of parameters that maybe you can then understand the problem. And this is an extremely common theme in math. I cannot tell you how many different core subjects of math have this substitution concept. And I'm not going to start naming things because it'll be a waste of time, but it's all over the place. So the idea is if you see something that if you did this substitution, it would look like x squared plus 6x plus 5 or x squared minus 2x plus 1, and that you would be able to factor that. But the original problem wouldn't look as simple. It might be like x to the 4th plus 6x to the 5th plus 5. So you might have bigger exponents. Or you might have weirder things like a x and then a plus 2 square root of x plus 1. And you might go, well, that's a square root, so let's go back to the last step. Well, in fact, it's actually in quadratic form, so you have alternative methods that you could use. So the idea is we make these two statements. The first one being let u equal the middle term's variable factor. Do you have to use the letter u? No, you can say y or a or b, or you can go into Greek letters, theta or phi, or all the weird ones like chi. But the reason we use u is because it's the second letter of substitution. The first letter s kind of sucks as a variable because s looks like a 5. So you let u be the middle term's variable factor. Now, these middle terms usually have coefficients to them. What I'm saying is ignore the coefficient for this part. So if the middle term was 5x to the 10th, you would say let u equal x to the 10th. You wouldn't have the 5 as part of that. Then what you do is you'll square that, and u squared, if you are correct that it's in quadratic form, should end up being the leading term's variable factor, again, ignoring the coefficient. Then what you'll do is you'll turn this equation into something in u, and you should get something like au squared plus bu plus c, where a, b, and c are your coefficients. And then in this course, I'm guaranteeing that you can solve by factoring. In the real world, you might need the quadratic formula or completing the square, whichever you prefer. But because there's more work after this, it would be an insanely more difficult challenge to have to solve this last part if it wasn't factorable to begin with. Just trust me there. I'm making this easier for you. We are making this easy for you. It's a general 161 rule, not just mine. So once you solve, you're going to get u equals maybe 2 and u equals 3. But the problem is, I gave you a question in terms of x, and you've answered it in terms of u. That's like me giving you a question in terms of dollars, and you answer it in pesos or in yen or in euros or whatever other currency. I'm going to go, well, I don't understand that currency. You need to do the job and go back to the standard American dollar, because if I ask you a question in dollars, I want the answer in dollars. So that's what this last bit is about, and we're going to go through all these steps. Go back to the let statement where you had u equals blah, 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 and you'll plug in the u values. You'll have numbers for u, maybe 2 of them, maybe 3 of them, maybe 1 of them, and you'll plug them in one at a time, and you'll have a little mini equation that you have to solve for x. Now that mini equation may be as simple as moving something from side to side. You may have to take a plus or minus square root. You may have to square both sides. All of the scenarios we've seen so far can creep up. So this type of problem is kind of the end-all be-all, because all the previous types we've done can show up in the process of solving this one. I'm not going to do every single one of those types. For instance, I'm not going to do an absolute value one. It's kind of arbitrary. But I will cover 2 of the other types. Okay, so example 1. And of course, check is necessary depending on what you originally had in your equations. Solve by substitution. Now, I said solve by substitution, so technically you're supposed to follow my instructions. Does that mean in the grand scheme of things that substitution is the only way to solve it? No. And in fact, the third one that we're going to do, not one, this is example, it's one for the day, but it's really example 5. I lost my train of thought. The third one we're going to do, example C, spoilers, it will have a square root in there somewhere. We will solve it by a substitution, but I will also talk about how you could have solved it in a different way, and that would have been perfectly fine. And again, in terms of testing, if you get the answers right, I won't care. But if you don't follow instructions, if it said to solve by substitution and you didn't do it that way, I would reserve the right to take some points away from you, or not give you full credit or not give you any points, something like that. That would be me taking points away, because like I said, if you get it right, that's fine. I'm not going to hark on you for that. Hark. I won't fuss at you or punish you. There we go. Words. All right. X to the 4th minus 5x squared plus 6 equals 0. Now again, I'm trying to set these up to be as simple as possible for the concept. There could have been like terms to combine, there could have been distributions to do. I may have had to move everything to one side. I just want to focus on these steps. That way, maybe in a homework problem, they have 1 or 2 extra things you have to do, and you do that, then these steps. All right, so what's the condition that something is in quadratic form? Because most equations are not in quadratic form. If the leading term's exponent, which in this instance is a 4, is twice the middle term's exponent, which in this case is a 2, then it is in quadratic form. Well, 4 is twice 2. 2 times 2 is 4, so it's in quadratic form. I don't want all that ink there permanently. Okay, so that means we can do this substitution concept. So I'm going to go to the side. So the side. And I'll say let u equal, and it's supposed to be the middle term's variable factor. So this is the middle term, but the variable factor is just the x squared. So that's what we let u equal to. Let u equal to x squared. Now this is assuming that everything is in descending order. If maybe I have the x squared term first and the x to the 4th term second, well, that's on me to fix that. So if I let u equal to x squared, that's a semicolon, just saying over here something else. U squared, so let's find out what u squared would be. And all we do is just take the right side. All we're doing is squaring both sides of this. We're just squaring both sides of the let statement. Not breaking any rules of algebra. We're just squaring both sides of the let statement. So again, I'm squaring both sides of the let statement to get what I'm about to write. So u squared, well, this is x squared squared on the right. I'm not adding these exponents, I'm multiplying. Now, it's a coincidence that the answer is the same. That's not always the case. So we're multiplying the exponents in that situation, which is u squared is x to the 4th, which is the variable factor from the leading term. Everything is working out perfectly so far. So this little double arrow, whatever you want to call that, this is me saying I'm transforming this equation into a whole new set of variables. In blue ink, I'm going to show the substitution. So instead of writing x to the 4th, I'm going to write what x to the 4th is equivalent to, which is u squared. We need to turn all x's into u's. So this is now u squared. The x to the 4th is now u squared. Then the minus 5, oh, wrong color. Black, there we go, minus 5. Now this x squared is what we have called u now. X squared is now u. We're just putting pieces into a puzzle. And then plus 6, there's no variable there, so there's nothing to do. So this is the transformation. We have changed variables. We've changed dimensions, as some people like to say in fancy language. I'm just going to rewrite this so it's all in one color. U squared minus 5u plus 6 equals 0. What do we do next? After we got this in u squareds, we solve by factoring. I have promised you in this course these will be factorable. All right, to the side, the leading coefficient's a 1, so I'm going to shortcut it. We take this number and its sign, the plus 6. We're going to list all the numbers that multiply to it, 1 times 6 or 2 times 3, in pairs, of course. And then we find the pair that adds, be careful, because you might subtract them. Oh, 6 minus 1 is 5. That works. Nope, because 6 plus 1 is 7. So because we're adding them, we actually choose the 2 and the 3 to make the 5. But that's a negative 5, so we can't make these positive 2 and positive 3. They need to be negative 2 and negative 3. So the factored form is u minus 2 times u minus 3. And that's still equal to 0. And then we zero product rule this. We set each of these things equal to 0 separately. So u minus 2 equals 0, and u minus 3 equals 0. All right, so what do we do next? Well, these are very simple to solve. We're just going to add 2 to both sides. That was weird. It didn't change color. Add 2 to both sides. And I said I will not always show these steps anymore. Add 3 to both sides for the other one. And you end up with u equals 2 and u equals 3. And some people like to box these up and ship them out, and then they get it wrong. It's wrong on the test, it's wrong on the homework, because these are not the answers. You might go, oh, we're supposed to check them, right, Mr. Beckner? No. Well, maybe, but no, that's not the issue here. These answers say u equals. These are pesos or yen or euros. Our problem was in X's, the standard American dollar. I don't want an answer in U if I ask a question in terms of X. You've got to speak the same language. You've got to use the same denomination. So at this point, we must go back to X's. How do we do that? We're up here now. Using the let statement, plug in the values that you found and solve the new equations you get for X. There might be one answer to each of these equations. There might be more than one answer to each of these equations. Some of them you might have to check and they'll fail or work. I don't know. So let's try this out. So in the U statement, the let statement, this is what we're plugging in. So we're going back to this thing, and we're going to be plugging numbers into the U because that's what U is. So one time we'll make the U2, solve that equation, and one time we'll make the U3, and we'll solve that equation. All right, so for the U equals X squared, this first one will be 2 equals X squared. Again, I've just plugged the 2 into right here in the let statement. That was our substitution equation. I like to call it a pivot point sometimes. And let's just focus on one thing at a time. Let's solve this. All right, so I'm going to do this wrong initially. With a number equal to X squared, you just have to take a square root of both sides, right? Because it says X squared. The opposite of X squared is square root. So we have 2 equals X squared. This is wrong temporarily. This is wrong temporarily. This is wrong temporarily. We just take a square root, right? Question mark. This is what I would say 80 to 90% of my students are doing before they get this embedded in their brain, and a good habit. You have to do things over and over and over and over and over to make them work properly, to get them right properly. What have I done wrong? I did not take a plus or minus square root. So I'm about to correct this now. It was supposed to be plus or minus square root. Now you might be saying, Mr. Beckner, the plus or minus is on the left side, not the right side. You've never done that before. That's because the number is on the left side this time. The plus or minus goes with the number. So this is correct. So what we'll get is, with the square root of x squared on the right side, that's now just an x. We don't know what the square root of 2 is. We cannot break it down. So that's plus or minus the square root of 2. There are actually two solutions in that box, positive square root of 2 and negative square root of 2. And those are accurate answers. For this next one, for the u equals 3, so again, we're going to the let statement. We're turning this u into the number you see. It's 3 now. So we go 3 equals x squared, and the equation solving will be identical. I'm going to make that same mistake initially. Oh, we just take a square root of both sides, right, Mr. Beckner? Well, you're close, but unfortunately, you've missed the mark very, very, very much so, even though it's close. You got to have the plus or minus, and now it's right. When you have x squared equal to a number, or anything squared equal to a number, it's plus or minus square root. It's plus or minus square root. It's plus or minus square root. I know I'm a broken record, but I have to be. Are you okay, buddy? Hold on a second. Sorry, everyone. Sorry, my dog was trying to tell me something very important. All right, sorry about that. Per usual, the fun of being at home. Okay, so the square root of 3, we don't know it, so we leave it as the square root of 3. But don't forget the plus or minus. Darn it, color. Plus or minus square root of 3 equals the square root of x squared is x. Since there's nothing else we can do to that, that's our answers. I don't know why I just put one of them in blue and one of them in black. I'm not going to change anything except the color. There we go. That is 4 answers. If you stopped here, you thought there was only 2 answers. And you might think, well, oh, 4, that's a lot of answers. We haven't had 4 answers to something before. That doesn't mean you can't. You can have a million answers to an equation. In fact, I very briefly mentioned something last class that the largest exponent, the leading term's exponent, this dictates how many unique answers you can have up to. So we can have up to 4 unique answers, and we ended up with 4 unique answers. There could have been some repeats potentially, but not in this instance. So x to the 4th, x squared, because those exponents, one of them was twice the other, that told me this was in quadratic form and I can do a substitution. So we make our let statements. I do suggest writing these down initially. If you get to the point after doing dozens that you don't have to and you can go straight to this, that's fine. Some people actually learn how to go straight from this to, and they just do this factoring in their head and the substitution in their head, and they'll go straight to x squared minus 2 and then x squared minus 3 equals 0. There's actually nothing wrong with that. And then you can set each of those equal to 0, and you'd end up getting the same thing. You get x squared equals 2 and x squared equals 3, which would give you x equals plus or minus square root of 2 and x equals plus or minus square root of 3. They have inherently done the substitution. It's just implicitly set up. There's nothing wrong with this if you know this more advanced style of factoring, but I don't like to assume that people know that advanced form of factoring. It's something that we used to always teach in our Algebra 1 equivalents, but I haven't seen it done in a long time. So again, I don't like to make assumptions. B, am I gonna have enough room? Yeah, I can make this work. B. All right, x to the 4th, let's do one very similar. X to the 4th minus x squared minus 12 is equal to 0. Again, keeping it simple up front, no like terms to combine, no distributions, no foiling to be had, no moving from side to side. Just ready to get down to the point. Gonna go a little quicker this time. Let's see if we can keep the first one up as kind of a guide, since I can't have the instructions up here at the same time. So first thing we did was this side. We noticed that this 4 and this 2 is 2 times 2 is 4, so it's in quadratic form. So we can say let u equal x squared, and this is the exact same thing, so u squared would be x to the 4th. Let me just verbally say another scenario. If this first one was an x to the sixth and this middle one was an x to the third, then your u would be x cubed and the u squared would be x to the sixth. If this was x to the 10th minus x to the 5th, your u would be x to the 5th, your u squared would be x to the 10th. It's just simple as doubling the exponent. So now we're going to transform this equation to, instead of x to the 4th, we write u squared. Sorry, I'm going down a little too much. Then minus, there's no other number there, so the x squared, we now write u. And then the minus 12 equals 0 stays minus 12 equals 0. We're going to take this minus 12 and take it to the side because this is another trinomial with a leading coefficient of 1, so we can shortcut it. Remember, if there was a number in front of u squared, this would work a little differently. It's the AC method or trial and error. So factor pairs of 12 are 1 times 12, 2 times 6, or 3 times 4. We're trying to find the one that has a difference of, what number is this right here? You don't see it. It's 1. It's minus 1 specifically. Well, 12 minus 1 is 11. 6 minus 2 is 4. 3 minus 4 is 1 though. So that's our choice. To make sure they come out negative, it's a positive 3 and a negative 4. Your arithmetic skills need to be up to par. So the factored form is u plus 3 times u minus 4. That looks awful because my u's and 4's look similar. Let's be a little more careful. U minus 4, we'll go with that style 4, equals 0. Set each of these equal to 0, you'll get u plus 3 equals 0, and you'll get u minus 4 equals 0. Now that one looks like a 9. I know you wish you had a teacher with better handwriting. That just looks awful. There we go. Subtract 3 on both sides, add 4 to both sides, you'll get u equals negative 3 and u equals positive 4. These are not our solutions though. We have to again go back to the standard American dollar, the X. Now I'm going to run out of room here, so let's just take this up here. So we said u is x squared, so we're supposed to be plugging the u values in right here. We're not plugging it into x squared. We don't know what x is. We know what u is. So for the first one, we get negative 3, color, negative 3 equals x squared. The second one, we get positive 4 is equal to x squared. For negative 3 equals x squared, same as last time, we're going to take a plus or minus square root of both sides, plus or minus going on the numeric side only. We're going to do the same thing to the other one. I'm going to show all the work at once this time, just in the interest of time. Okay. The square root of negative 3, I don't know the square root of 3. I can't break down the square root of 3, but I know whenever we see a square root of a negative, we pull out an I. So this is going to be plus or minus. The I has to go after that, not in front of it. And then square root of 3, that's equal to square root of x squared is x. Now you can have imaginary solutions. This is perfectly fine. Square root of 4 is 2, so that's plus or minus 2 is equal to x. So we got 4 unique solutions again. They don't have to all be unique. There can be repeats. Now you might say, well, Mr. Beckner, you didn't check your solutions to either of these, and I saw a square root somewhere. Well, you saw square roots because we took a square root. It wasn't embedded in the original problem. There is no reason to have to check polynomial solutions as long as you didn't make any boo-boos along the way. Now, maybe you made a boo-boo. I don't know. I can't tell what you're doing on your own. This solution is going to be a little bit more difficult to check, especially since we haven't talked about what I to the 4th is, but you could just square it and then square it again. That's the idea I have mentioned. So A and B are extremely similar to each other. Even if I had made these x to the 6 and x cubed, the u parts would have all been pretty much the same. It's just here we would have had x cubed equal to negative 3. We would have taken a cube root of both sides, and you never plus or minus with cube roots. It's only even roots. All right, so with 2 similar problems out of the way, let's mix it up. let's get a little weirder and go with x plus the square root of x minus 30 is equal to 0. So this is drastically different than the last pair. And what some students might notice is they say, oh, this is a square root equation. So I'm going to go back up to this style problem up here and do it this way, where I isolate the radical, raise both sides to a power that matches, which would be squaring in this instance. There'd be no plus or minus because it's the opposite scenario now. Step 3 and for that problem wouldn't be necessary, just FYI, and then they'd solve it and check the solution because they'd have to check it. So these instructions are 100% valid for the problem that we're about to do. And if a student did it that way and got the answer right, that's perfectly fine with me. But if a student did it that way and got it wrong and the instructions said to use a substitution, I would not be inclined to give them partial credit, even if they requested it, and even if they made just like one simple mistake in their alternative method. Again, partial credit's only valid if you follow instructions, which I said, I'm okay if you don't follow instructions as long as you can get the answer right. I know that almost sounds hypocritical, but I don't find it to be. At least I'm not the teacher that always says, if you don't use the method, then I won't give you any points even if it's right. I'm not doing that. All right, so let's see. The whole idea for this method to work is the leading term's exponent has to be twice the middle term's exponent. And you're looking at this and going, well, that's not the case. This is a 1 and this is a square root. How can you even compare those? Well, here's the thing. The square root of x is the same thing as x to the 1/2. We just went over that rule earlier. So this exponent is really a 1/2 when you think about it that way. This exponent is a 1, and guess what twice a half is? You're right, it's 1. So this is actually in quadratic form. The other idea to be in quadratic form is that if you square the middle term's variable pieces, you get the leading terms. And if you were to square a square root, guess what you get? You just get the inside, which is x. So that also confirms that it's in quadratic form. Doubling the exponent is the same idea as squaring it. All right, so what do? We say let u equal. Now, even if I had a number right here, if I had a 7 in front of this, which I'm going to erase in a second, I would still say let u equal the square root of x. 7's not really there, but I'm just pointing that out. So if u is the square root of x, u squared is, remember, to figure out this, you just square both sides of that let statement. If you square both sides, the square root and the square root will cancel, giving you just an x. So as weird as this one looks, it is actually in quadratic form. Now, do I expect most students, in all honesty, to, if there were no instructions on which way to solve this, to do it with quadratic form? No, I would say most of them are probably going to move the x and 30 to the other side and then square both sides. But it's a good technique that works. It is still possible to factor this original equation, but you're going to be factoring using irrational variables. So it's probably going to make your brain melt a little trying to do that. I would not suggest it because, so like, remember when I did that side stuff? Oh, I erased it. That's right. On this one where it was like an x squared as the leading bits there, what it would be this time is it would go straight to square roots as the first term in each of those. Basically, whatever the variable factor looks like here is what goes in the first spots. So that's the kind of shortcut there if you like that concept, if you understand it. All right, but I will do the full-blown method as we've discussed. So instead of x, x is u squared. So this is now u squared, then the plus. Instead of writing a square root of x, that's really a u. The minus 30 is still minus 30, 0. This is factorable. If you write all the factor pairs of negative 30, that's 1 and 30, 2 and 15, 3 and 10, or 5 and 6. We're trying to find the pair that subtracts to 1, so we choose the 5 and 6. This time the difference needs to be positive, so it's negative 5 and positive 6. Arithmetic has got to be on point. So that's u minus 5 times u plus 6 equals 0. Then we zero product this rule, excuse me, so that's u minus 5 equals 0, or u plus 6 equals 0. Add 5 to both sides of the first one, you get u equals 5. Subtract 6 on both sides of the second, and you get u equals negative 6. And then somebody boxes these up and ships them out, and they're wrong, wrong, wrong. Because this is in yen or pesos or whatever currency you like, rubles. We got to go back. We got to go back to our standard currency. So instead of writing u, we write the 5 equals square root of x and the negative 6 equals square root of x. So 5 equals square root of x. Again, I've just plugged it in here. The u went there. And then negative 6 is equal to square root of x. Now, I'm going to focus on these one at a time for a reason. So for the first one, with 5 equals square root of x, is this what we're going to do? Do we plus or minus square both sides? Question mark, question mark, question mark? No, we don't. We're close, but there's no plus or minus needed in this scenario. We just square both sides. Make sure you have those tactics down. 5 squared is 25. Squares and squares cancel, so you get 25 equals x. Now, if you box this up, you need to be careful, because really we're not sure yet. Why are we not sure yet? Because the original equation had a square root in it. Because the original equation had a square root, this was one of the types of equations we've learned so far that we have to check. We have to check this one. So we have to check it. So before I'm just gonna keep to this one for now because the second one's kind of special. So to check it, we take the solution and we plug it back into the original equation. We got to plug it in here for the x's. So the 25 will go here and here. So 25 plus square root of 25 minus 30 is that 0. I'm gonna need to get myself a little more than that. There we go. So 25 plus the square root of 25 minus 30, is that equal to 0? Square root of 25 is 5. So 25 plus 5 minus 30, is that 0? Well, yes, it is. So x equals 25 is a solution. Perfect. Maybe there's another one. Maybe there's another one. Maybe. So what did we do when we had the square root equal to a number? We squared both sides. And then you would get x equals 36. So the work that I'm about to actually write down is not what I'm saying. Okay, so once again, the work that I'm going to write down is not what I'm saying. If you went to solve this, if you try to solve this, you're going to square both sides. I'm going to erase this after a minute. That squaring on the left looks wrong though because it's got a negative. When you square both sides, you'd get 36 equals x, and then you would check it. And if you check it, 36 plus the square root of 36. The square root of 36 is 6. 36 plus 6 is 42. 42 minus 30 is not 0. It will fail, which means you toss the solution out. So really there's only one solution. Now it is perfectly acceptable to have solved it that way, but it's a little more work than what I have to do. Instead, what I can do is an analysis. The same analysis that we have done more than once already in this course. We did it with square roots and with absolute values. This left side is a negative number. This right side square roots, no matter what, when you take a square root, it's always positive, or it's imaginary, but we're only thinking about the real parts here. It can't be negative. Negatives can't be positive. That's a false statement, which means there's no solution. So again, the thing that I wrote before and then erased is if you try to solve it, which we did, it won't check. Again, I'm referring to only that one. So there was one solution, not two. Up here, you probably thought there was two solutions. And again, some people would have stopped. But it's not, because one of them, once you transform it into x like you're supposed to, it doesn't check. Now, if you're not checking your solutions when you're supposed to, you might say 36 and 25 are the solutions. And then my math lab is going to mark you wrong. And you're going to be upset. And again, in terms of a test, if you point it out, I can give partial credit, but definitely not full credit. You have got to know when to check your solutions. If you don't know, check them anyways. Check them all the time. Polynomials don't need to be checked. This was not a polynomial. This has a radical. You need to learn the different classifications. I'm not saying you have to learn them by name. It's really a great idea to, of course, but you have to learn, all right, it's got this thing. This thing says it's not a polynomial. I have to check the solution. Whereas the previous two examples didn't have square roots. They didn't have absolute values. They didn't have any fractions with variables and denominators. So they didn't have to be checked. I never checked them. They would all four check out for each of them, but I didn't have to. All right. Excuse me. So that is it for this section. Are these the only types of things in quadratic form you can see? No. There's a variation you might see, which again, I don't do every single type of example. You might have something like a 2x plus 3 squared plus 5 parentheses 2x plus 3 plus 6 equals 0. This is in quadratic form, and you might say, oh, I don't need to do all that. I could just take this parentheses and FOIL it, distribute this 5, combine like terms, and then maybe it's factorable, or maybe quadratic formula, or complete the square. Sure, you can do those things, but it's going to be way, 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 way longer than just saying let u equal 2x plus 3. That's the middle variable factor, because those things are identical. The exponents are a 2 and a 1. You can take a shortcut. I would say, I don't know, 50% of the time, if a problem's in quadratic form, there's another way you could solve it. But usually when something's already in quadratic form, it's going to be the quickest way to solve it by doing this let stuff. So, sorry for that. Not going to solve that one. Are the solutions pretty? 2 and 3. Yeah, you could solve that. I'm not going to say what they are, but this is pretty easy to solve. You'll get u equals 2 and 3, and then you'll have to go back and solve it for x, which is pretty simple. There's not even any square roots or squares to do all that. So we'll call it a closeout for 1.6. So we have finished that section, which means we are ready for 1.7. Now, I'd like to remind you that, and I'm even going to show you in my notes, I still have it labeled as 1.8 from before we changed additions, I want to say in the spring. We may have changed in last fall, in fall of 2019, but I didn't teach this class that fall. I think I didn't teach it till the spring. So again, this what this material is used to be what we call 1.8, but now the chapter stops at 1.7, and they threw this in chapter 3. So this is really 3.6, not 13.6, 3.6. All right, so just so you know that 3.6, reminding you that it is part of the same chapter. For us, at least, metaphysically, I guess. 1.7, I don't know why that's the smallest font. That's weird. Linear and absolute value inequalities. Linear and absolute value inequalities. So there was something that was back. There was something that was back in the prereq material. I think there were some examples I gave you in that assignment on intersections and unions. And I said, while I did touch bases on a couple concepts there, I said a lot of the bases I was only going to touch on once we got to it, like factoring. I didn't really address factoring until we got to the heavy-handedness of it in 1.4, I think, something like that. So this is another one of those cases. So this is something that you may have been taught. You were supposed to have been taught, arguably, in a previous algebra class, What is interesting, and I can say definitively, at TCC, we don't teach this before Math 161. So it's kind of a catch-22. But anyways, it's a simple idea that throws a lot of people off until they practice it 5 or 10 or 15 or 20 times, just depending on how much they have to practice it. First of all, your interval notation. That is something you would have seen. I was talking about the intersections and unions, so let's get to that later. Interval notation is another way of describing something that's on a number line in 2 dimensions. So, for instance, let's draw this up as the inequality then the number line, and then the interval notation, IN for interval notation. So an inequality like x is bigger than 5. On a number line, what this would look like, here's your 5. That's the only number I'm going to label since I'm doing this by hand. Greater than means you shade to the right, so you would shade to the right. I always like to put arrows on the ends when I'm doing this by hand, signifying that it goes to forever, to either positive or negative infinity. Now, you may have come from a class where you did open and closed circles. In this instance, it would be an open circle, but that's not the notation I'm going to be using. We'll still use that notation on 2-dimensional graphs, but what we typically like to use at this level is parentheses and brackets. So parentheses is used whenever you have a greater than or a less than. Greater than means, or less than means, that that number is not included. So this is known as exclusive. It excludes the 5. 5.0001 would be included, but not 5. 5.0000000001 would be included, but not 5. So this parentheses is the symbol for saying 5 is not included. In interval notation, so interval notation always goes, if you were to do the number line first, the furthest left that's shaded, then a comma, that comma is part of the notation, then the furthest right that's shaded. And then you'll put parentheses or brackets around the outside numbers, depending on the case. Now above that I say that for infinities, you are always going to use a parentheses. 100% of the time, whenever there's an infinity, the infinity gets a parentheses. You will never ever bracket an infinity. Brackets are when you include a number, when you can touch it. An infinity is this theoretical number that's always out of our grasp. It's kind of like the pot of gold at the end of the rainbow. If you go hunting for it, you're never going to find it. It's always out of your reach. So interval notation. The furthest left number that's shaded up here is a 5, then a comma. This is shading right forever, which means it goes to infinity, specifically positive infinity. Then the 5 and the infinity get parentheses or brackets, and they could be different or they could be the same. This 5 had a parentheses because it did not have the or equal. It's going to be consistent. Infinity always gets a parentheses. Let's do a few more of those really quickly. So x is greater than or equal to 5. Come on, Rambo, stop shaking my table. My dog's scratching under my table now and he's shaking it really badly. Come on, buddy. Be a good boy. All right. So number line, still a 5 up there, only number I really need. Shading to the right because it's greater than. Arrow saying that it goes forever, never, never. And in my math lab, clearly you're not going to be doing this. It's a multiple choice kind of thing, which is not my favorite. I really do prefer all this stuff done by hand, but well, we got to do what we got to do. Now, because it has the or equals, that means that number is included and the bracket is the symbol for including a number. If you were more familiar with the circle method, this would have been a shaded circle. Now, that is still an important idea to have because it will be used in 2 dimensions, as I've already said. We'll get to that another day. But for now, bracket. The interval notation still goes 5, comma, infinity. That furthest left is still 5, the furthest right is still infinity. You still parenthesis the infinity, but you have to bracket the 5 because it had the or equals. One thing I always associate, the or equals is a straight line, brackets is just connecting several straight lines. I don't know, worked for me. If we had x is less than or equal to 3, doing these really quick, number line 3, less than, so shade to the left. Arrow going left forever to what we call negative infinity. It has the or equals, so we bracket it. The interval notation, the furthest left is not 3, it's not 3 comma infinity, this is wrong, wrong. The furthest left is negative infinity, we're going left forever. The furthest right is the 3. Your orientation is extremely important. We bracket the 3 because it was included, we parentheses the infinity because they're never included. If you get these numbers swapped, there's no partial credit for something like that at this level. You've got to have your interval notation down. The interval notation is prereq material. You should have done that in a class previously. It's the unions and intersections that I said, you probably didn't, especially if you came from TCC. X is less than 3, however, number line, 3 in the middle, shade left, parentheses the 3 this time though. And then it's negative infinity up to 3, both with parentheses. You could have compound inequalities, which means the x is between two numbers. So something like negative 3 is less than x is less than or equal to 10. So now the number line, I'd need two of numbers up here, a negative 3 and a 10. Make sure these are oriented correctly because I could have said 10 is bigger than or equal to x is bigger than negative 3. Literally the exact same statement, just bass backwards. I didn't say a bad word there, so I think it's okay to record that. It's just everything would have been flip-flopped. Then the x is between those numbers, so you shade between the numbers. We're not going off to infinity this time. The negative 3 gets a parentheses because no or equals. The 10 gets a bracket because it had it. Then the interval notation is just from negative 3 up to 10, bracket the 10, parentheses the negative 3. We can also see, last one, something like this. X is less than 12 or x is bigger than 50. This is a solution with a gap, and this is something that might be new to you. So the numbers I need up here are 12 and a 50, and I have to put them this way. The first one says x is less than 12, which is this is our solution going left. The other one says x is bigger than 50, so this is the solution with an arrow going right. Both of them have parentheses because neither had an or equals. Now, the solution here in interval notation, I cannot do until I go a little lower completely. There's going to be a symbol I'm missing. But basically, you just need both of these sections. So the first section over here would be going from negative infinity up to 12. So negative infinity, comma, 12. We will parentheses both of these because there's no brackets at all. The second solution, and they have to be in this order, you have to put the less number on the left and the greater number on the right. So the other one is 50 to infinity, again, both with parentheses. And some people might say, oh, we'll just write the word or here. I mean, outside of class, that might get you by perfectly fine. But inside of class, we have a symbol that we need. An intersection, which is an upside down U, is the overlapping region between two or more inequalities. That's not what this is. That says overlapping regions. None of this was overlapping, so clearly that's not what I'm talking about. A union, this is what I'm getting on, which looks like a regular U, the upside, so I'm saying an intersection, when you want to use that in a set notation, intersections, you'll be drawing that, whereas unions, you'll draw this. You don't actually put the back on the U. So this top one is the symbol for an intersection, which is an overlapping region. A regular looking U is a union, which is the combination of two more regions that are separated. So here's two or more regions that are separated. So the set notation that we have to throw in with this is that. That is our mathematical equivalent of saying or. So this right here is going to be seen semi-frequently throughout this course. You're going to see it in the next couple sections. You'll see it used in chapter 2 when we talk about things like where is a function increasing, decreasing, or constant. And when you get to calculus, you'll see it used periodically there as well. So this is when we have a solution that's got a gap to it. The union is basically just saying, hey, it could be this one or it could be this one. They're both valid. Kind of like before we were saying x equals 5 and 12. So before I actually get into any examples with these, let's just practice this union and intersection stuff, what some basic problems would look like. So example, let's write that. Example, find the intersections. Example 1, of course. Why did I make a semicolon instead of a, there we go. A, black, am I on time? 20 minutes. All right, so find the intersection or union, whichever is advertised. So for A, actually we will do both. How am I doing it that way? Let's go 3, 5, unioned with, let's go with 4, 6, that way. So just doing whichever one I ask for, which I'll do the intersections and unions for most of them at least. 3, 5, so these are in interval notation, and then union with 4, 6. So I'm going to do the 3, 5 on a number line. So the numbers I need are 3, 4, 5, and 6 clearly. 3, 5 I'll do in blue. So here's the 3, here's the 5, and there's the shaded region. 4, 6 I'll do in red. So we're doing this in red, we did this one in blue. 4, 6, that way we'll put a parentheses on the 4, we'll put a bracket on the 6, and we'll shade between them. So what exactly am I asking for? This was just drawing both of those segments on the same number line, and I want to write a simpler answer, because 3, 5 union 4, 6, there is a simpler way to do this. And the best thing you can do for yourself is graph it to visualize it. So remember, the union is everything. The union is the combination of the 2 or more regions you see. So it's everything that you see shaded. Now there's no gaps here, there's no gaps in this, so our answer is not going to need a union. There's not going to be any gaps. So let's do a different color. Let's go yellow or green. Green sounds good. So the union is everything. I'm now going to shade everything that I see. I'm starting at the 3, and I'm just shading wherever I have anything shaded, blue or red. It's everything. And then it was a parentheses on the left and a bracket on the right. So that green is the solution. It would be parentheses 3, 6 with a bracket. Unions are everything that has been shaded. Intersections are only the overlapping regions. So let's flip the script here and do 3, 5 intersected with 4, 6. I will admit, this is not a typical problem in pre-calculus. You will never see anything like this for the rest of our couple months together. But the concept itself is important. Whether you know you need to, with an application problem, whether you need to take everything or only the parts where both of them are. All right, so once again, let's number line. I think I'm only gonna have time to do one of these, by the way, so an A and a B. 3, 4, 5, 6. Don't worry about my infrequent spacing or uneven spacing. Red. So in blue, we'll do the 3, 5 again, which is exactly the same. In red, we'll do the 4, 6 again, which is exactly the same. Now again, for the previous one, for A, a union means all shaded areas. With an I just wrote an intersection, didn't I? I said the right word at least, but I was thinking about this problem. Union means everything that you shaded is the solution. With an intersection, that means it's only the overlap. That's the major change here. So what am I going to highlight in green? Do I highlight here? Well, this is only blue, so in fact, no, that's not part of the solution. Do I highlight over here? Well, no, that's only in red, so not part of the solution. The only section where I did blue and red was between 4 and 5. So that's the region we're going between 4 and 5. And then for the ends, you just have to think about your parentheses and brackets. Now, if one of them has a parentheses and the other has a bracket, you would have it as a parentheses for the green because it would only have been included for one of them. So that's a subtle detail to watch out for. But that wasn't part of this problem. These are both just parentheses. So this solution would be 4, 5, both in parentheses. That's the difference of a union versus an intersection when you're talking about, hey, we have these two different regions, but the solution can include all of them. Or we've got these two different regions, but the solution can only include the overlap. So there are problems where you can include everything. So you have to understand that you're doing a union as part of the bigger picture. And there are problems where it's only the overlapping bit that works. So you have to understand conceptually that you're doing an intersection. Symbolically in this course, again, we'll see the union a lot more, especially because we're going to be solving problems with answers like this bottom left one here that graphically look like this, and then an interval notation will look like this. So again, the union is the more common issue for us, but don't think you can discount the other thing. All right, 10 minutes. Space. Here we go. The first topic of 1.7 is solving linear inequalities. Something that you probably already have experience with, something I hope you already have experience with. So this should hopefully be nothing new, but we're probably going to de-rust a little. You treat linear inequality, well, you treat inequalities just like equations. So an equals means it's an equation. Having a less than or having a greater than or less than or equal or greater than or equal means it's an inequality. So we're going to treat them just like equations. Whatever you do to one side, do to the other. You will have equations that have inequalities that have 3 sides. In those instances, whatever you do to one side, you do to all sides. I have that memo down here. I'm kind of jumping the gun. But there's an if statement. This is the one minor change in equations versus inequalities. You do everything the same. Add, subtract, multiply, divide, square roots, squares, all that stuff, factor, except in the process of solving the equation, the inequality, I keep saying the wrong word. I keep looking at the word equation. That's my fault here. If you multiply or divide both sides by a negative, you must flip the inequality sign. So if I were standing in a room in front of you right now, what I would do also, if my right shoulder wasn't completely busted, but that's a story for another day, I would take both of my arms and I would stick them straight out so they were running parallel to the ground. So you'd be looking at me and I'm going, I'm a number line. And then what I would do, so I'd be facing you originally, and I'd say, I'm about to multiply or divide both sides of myself by negative. And what that means symbolically is I spin around 180 degrees. Whenever you multiply or divide something on a number line by a negative, you are flipping the number line 180 degrees. Negatives are positive, positives are negatives. So that less than orientation has to change with you, or vice versa. So should you ever multiply or divide both sides by a negative, you will have to flip the inequality sign. That is the one major difference in these. Also, I say to always move the variable to the left side. Technically speaking, this is optional, but I want you to do it anyways, because this is why. This will get erased in a second. X is greater than 3 is the exact same thing as saying 3 is less than x. So if you solve it this way, you're a lot more likely to get the graph and the interval notation wrong, because you're going to see this less than and you're going to shade to the left forever and ever and ever. But in reality, the solution oriented correctly is x is bigger than 3. Again, these are the same statements, just mirrored, which means you should have been shading to the right instead. So that's an important thing to get used to. Now, again, if you are advanced and can get it right without moving the x to the left, I won't punish you, but trust me, 80% of students that don't do this right here end up getting their interval notation backwards. So always move your variable to the left with these inequalities. And if you multiply or divide both sides by negative, flip the inequality sign. It's not just because there's a negative somewhere. It's because you chose to multiply or divide both sides by negative. Okay, so with that being said, let us get into there we go. Example 2. Solve graph, put in Raffi. What was that, the singer from like the 90s or the 2000s, Raffi? Solve graph and put in interval notation. Abbreviating there. Solve graph and put in interval notation. So I want all 3 types of solutions. I may only ask you for the interval notation. You may only be asked for the graph, but I want us to get used to doing all of them. A, we're going to have 3x plus 5 is greater than or equal to 8x plus 40. All right, so if this was an equation, I would definitely subtract 3x on both sides personally. But this is not an equation. So I'm going to stick with that. Always move the variable to the left side. So again, I'm going against my will if this was an equation, but it's not. I'm going to subtract 8x on both sides. Now, since I'm moving the variables left, that means the constants go right, so I need to subtract 5 on both sides. You can do that in 1 step or 2 step, it's up to you. 3x minus 8x is negative 5x, then is greater than or equal to, the 8x's cancel, the 5's cancel, 40 minus 5 is 35. I don't know why I wrote that a little higher. Go. Now the number in front of the x is negative 5, that's negative 5 times x, so we have to divide both sides by negative 5. It is this step right here that is the reason I must flip the inequality symbol. I chose to multiply or divide both sides by a negative. Now inherently, that's because of this negative right here. Because that was negative, I had to divide it out. So what we're going to get is, let me just go here. X on the left-hand side. The greater than or equal becomes a less than or equal to, and then negative 5 goes into 35 negative 7 times. It has nothing to do with the number on the right-hand side, whether it's positive or negative. It has to do with the variable being negative and you dividing or multiplying by negative to get rid of that. So this has changed directions. So that's the solution in inequality form. I wanted the graph of it. The reason I'm asking for the graph is because it's a lot easier to get the interval notation if you're staring at the graph. It's a lot harder to go from inequality to interval notation. You will probably learn that skill after you do it 100 times, but for now, let's just be detailed. All right, so we're going to shade to the left because that was x is less than. I like to put my arrow on the end, signifying that goes on forever. Because it has the or equals, we will put a bracket on the negative 7. Make sure it faces the shaded region. There's the graph. So the interval notation is furthest left, comma, furthest right. Negative 7 is not the furthest left number. This is a grand mistake people make. Negative 7 is the right number. It's negative infinity, not just infinity, negative infinity. That is on the left. Comma, then the negative 7. The 7 gets a bracket. Infinities always get parentheses. There are our 3 answers. 3 minutes left. We don't have enough time to do B. Spoilers, it's going to have fractions. I'll go ahead and write it down, and I'll give you a chance to do it before next class if you'd like. But it's going to be 3x over 5 plus 2 is greater than or equal to x over 3 plus 1. So we're going to solve this. It's got fractions, which makes it inherently a little more difficult. But remember, you do everything the exact same as with the equations. We had a trick with equations and fractions. We said find the LCD and multiply everything by the LCD to get rid of the fractions. So if you want to try this on your own, go for it. I'm not going to spoil the solution though. We'll leave you hanging on for that. Besides that, if you have any questions, please email me. Remember, we did finish 1.5, so it's due in a week. That due date is already set up.
That is the wrong class. Whoops. There we go. So remember, your 1.5 homework was due today. Your I think I meant to say 1.6 there. 1.6 is due in a week. And we will finish 1.7 next class. I think we'll even be able to get into 3.6, and that might confuse you, but we will explain that next time. 3.6 is actually part of chapter 1. They just changed the textbook around, and they shouldn't have, in our opinion, so we're keeping that as part of the chapter 1 material. But more details on that later. For now, have a good weekend, work on that homework. Don't forget the prereq assignment for those 5 bonus points if you haven't already done that. Email me with any questions, and have a good weekend. Take care.